Hello everyone, it's July 27th. Alright, the original goal was, we have two problems that we need to keep working on. One is yesterday's problem, which I want to try the Floyd-Warshall algorithm, which is a different way to find the minimum weights between any two nodes in a directed weighted graph. So I want to do this. I also want to try this one again, which is the smallest number of neighbors, which I want to use Dijkstra for this. So these two are kind of just in the mix, and now we have to do this for today, which is a tough question. Okay, tough question. Yeah, let's have no fear. Let's go for it. Second minimum time to reach destination. Just turn off the light. A city is represented as a bidirectional connected graph with n vertices, where each vertex is labeled from 1 to n inclusive. The edges in the graph are represented as a 2D integer array edges, where each edge denotes a bidirectional edge between u and v. Every vertex pair is connected by at most one edge, and no vertex has an edge to itself. The time taken to traverse an edge is time minutes. Okay? So basically the time is the same for all the vertices. That's what I read. Each vertex has a traffic signal which changes its color from green to red, and vice versa. Every change minutes. All signals change at the same time. It can enter a vertex at any time, but can leave a vertex only when the signal is green. It cannot wait at a vertex if the signal is green. The second minimum value is defined as the smallest value, strictly larger than okay, strictly larger than the minimum value. For example, the second minimum value of this 234 is 3. The second minimum 234 is 4. So given these, return the second minimum time it will take to go from vertex 1 to vertex n. Holy crap, you're kidding me. Second minimum time. Oh my god. Okay, so what it says is you'll cross it with the given time, and the signal changes every change minutes, and it can enter a vertex at any time but can leave when it's green, and when it's green you have to leave, right? So in this case we want to go from 1 to 5, so I can say I enter at 1, blue path, take it on the right is the minimum time path. So what does that mean? Time 1, still 1 minimum time. 1 to 4, 3 minutes, time lapse at 3. So yeah, you go. So there's always a green light, right? So you take 3, but how long does the green last? From green to red, and vice versa. Every 5 minutes will change. So the light will remain green for 5 minutes. So you can go here, take 3 minutes, and when it's here, because the current ticker is 3 and it's 5, right? It's because the green will maintain for 5 minutes, so immediately it can go. So it's 6 minutes. So the red path shows the second minimum time, start at 1. So go 3 is 6. Now it's red, so we have to wait. Because now it's 6, so I change at 10. So we'll wait for it to 10. So it's 13. Oh, you are kidding me. You can go back and forth. So it will change, so it will be 2, 4, 6, 8 is the time. 0, right? 0, 2, 4, 6. So we have an interval. So for the second example, the time it can go is 0, 2, 4, 6, 8, right? And then we start at 1 here, and we need to go to 2. And if I go to 2, we'll take time 3, and then we'll be done. Right? But we can go back to 1. Oh God. Oh God. I don't know. Holy crap. You literally going back, but you cannot go back because the time you go back is at 4. Right? You go back. So basically it's 4 plus 3. No, not 4 plus, you take 3, right? That's take 3. Then you wait until 4. Then you go back at 7, but you have to wait until 8. Then you go, so it's 11 minutes. So, okay, the question is, how do we determine the second smallest time? The second smallest time. How would you do the smallest time? Well, I mean, we can go, BFS to find the smallest path, right? We'll find the smallest path, and once we find the smallest path, then based on time and change, we can probably get to so I think the smallest path will be the smallest, or the shortest time will be the smallest path, right? Because otherwise you'll have to do more, and then you'll always end up longer, right? The time will always end up longer. So probably what we need to find is the path with we find all the paths, right? We find the shortest path, and we need to find, but that might take a lot of time to find all the paths. Yeah, basically, because at the end of the day, it doesn't really matter, right? It doesn't really matter. What we need to do is find all the paths from 1 to n. And then we need to find the one with the second smallest number of steps. That's it, right? And if we don't have a second smallest number of we don't have, right? If there's only one path from 1 to n, and then we just need to do a double, a back and forth, right? We need to add that. And in fact, if I know there is 2 steps, right? 2 steps, and we say the time is 3, and the change is equal to 5, then what we know is the allowed time is 0, 5, 10, 15, right? So we have 2 steps, which means when we get to the first stop, it will be 3, and then we can check. So now we get a second stop, then we're done, right? Now here we have 3 stops. So we have the first stop is 3, we check. Second stop is 6, we check. We'll move on, right? We'll move on. So we have, so the first step is 3, and move to the second step, right? Second step I need to wait to 10. So we have to wait to 10, and then go to the third step, so it'll be 13. So yes, right? Yes. Now we need to see the n. N is 10 to the 4. 10 to the 4. No duplicate edge. Basically what we need to find is, so how do we find the second smallest? Yeah, how do we find the second smallest path. So we can DFS. DFS. Is that a DFS problem or is that a BFS problem? So we can BFS will be the easiest to find. The shortest path. Now, once we find the shortest path, we can find it when target is reached for the second time. But the things might blow up. Okay, the things might blow up. Because you basically in 1, the second level you add 2 and 3. Okay. And the third level, what do you do on third level? Do you add 1 again? You have to add 1 again, and you add a 4. And then you have to add, 1 and 3 again. Right, so it blows up. Right, it blows up. Yeah, then the question is, how do we how do we get there? How do we find the second smallest? Yeah, this is really tricky to find the second smallest. Let's say we have, a path. Okay, let's say from 1 to n. We have a path which is the smallest. And then there is a second path to reach it. But how? Maybe what you can do is we take 1 away and see if there is a path to it. Right? We'll see if there's a path to it. And if there's a path, then we record it. If there's no path, then yeah, we cannot do it. Yeah, we cannot reach it. And then we break this, so we break it 1 at a time. So at least one of them cannot be used. Well, we can do that. I mean, yeah, we can do that. But is that the right way to do so? Right? Is that the right way to do so? Is that the right way to do so? We break it, so we have to run it again. So now the runtime, it'll be O(n), because we have to go through everything. And so another thing to keep in mind is, if there's no other, we just need to go back and forth. We basically is the smallest plus 2, right? So we find the min, we can always plus 2. Like this 1 plus 2 is 3, right? 1, 2, 3, right? We do 3. And yeah, because it come here is 3, and then we'll change a 2, so we have to go at 4, right? We have to go at 4. Yeah, if it's bigger than this, we have to find the next one. So yeah, so like this one just plus 2, but that's because there's only one way. So now the question is, how do we already have O(n), and if it takes a long time, if we can't just go through everything. We need to find a way to see if there's another path, right? To see if there's another path. And we also cannot just keep piling up. Let's see when is the second time that it happens, right? When is the second time that it happens? Well, because we have a plus 2, right? So what we need to find is min plus 1. Is this possible? Is this possible? Okay? So what does this mean? Well, this just means for each node, we'll do this. Right? Because if this is the smallest, that's actually not true, because I can do this. Right? I can do this. Okay. Let me see. So what we want to know is if some node can be hit, because if we do BFS, right, each node, we can find the earliest time that a node can be hit, and then we note it, right? We note it at which step, right? And if the next time when a node gets hit, it can only be +1, right? It can only be +1. If a node gets hit +2, then now we don't want it. So it is BFS, right? It is BF, but we do a +1. If it's +1, we allow it, right? So like in this case, this one gets hit. Originally it's 2 steps, but now we get 3 steps. We have it, right? We have it. And then we go to the end to see if we can have a min +2, min +1. If we have a min +1, that's the result. If we don't have it, then it's okay. That is a idea, and we want to entertain that idea and see if we can get this one. I think it's very neat. I think it has a lot of potential. We'll see if we can get it. Let's see. So of course, first of all, we need to get a boolean, right? It'll be interesting that we're doing boolean graph new boolean n. Okay, n +1. Doesn't matter. Okay. For int e of edges, we simply say graph e0, e1 true, graph e1, e0 true. All right, so we have the graph. Next we need to do is BFS. Okay, so well, we can probably just write it here. So now we're gonna do BFS for min steps from 1 to n, and second, and min +1 steps from 1 to n, right? So I need to say min and VFN. Oh, oopsie doozy. Okay, so for min and VFN and the min plus. Okay, so int steps goes to new int n +1. All right, we need a queue, which we don't need to use a queue. We can just use a linked list. So I can say queue. I needed step, so I say int this queue equal new linked list. Okay. Then I say queue dot add new int, which we're gonna put 1, and it's levels, right? Level. So then we can use level to find that. All right. And basically, we'll do min steps. Okay, we'll do this is min steps. Okay, now we say while queue is not empty, right? If queue is not empty, and now I'll push it out and say int element equal to queue dot pull, right? So we pull it out, and We have the current level. Then we say for, holy crap. We have to go through every single one? That seemed to be a bad way of doing this. I don't like it. I do not like it. I do not like it at all. Because that means we have to go through all n in order to find where my child is. I think that takes a long time. Okay, I'm going to change this. Change this into a map integer and a list of integers. Sorry, I kind of don't want to do it this way, but there's no way to avoid it. So new hash map. Okay, and these are all wrong. Now we shall say graph dot add put if absent e0. Okay, new array list. Oh shoot, new array list. Okay, and graph dot put if absent. Okay, this is going to be e1. Same thing, new array list. And graph dot get e0 dot add e1. And I'm going to do the same thing for the next row, which we're going to call it get. This is going to be e1, and it's going to be e0. Okay, so now we can say for int child of graph dot get element 0. Okay. So for each child, I need to check. Right? I need to check if it's just +1, then I'll do it. We can say if it's 0, right? We say if if min steps child is equal to 0, or min steps child +1 equal to, so it means the child is not 0, right? But the next step. Okay, I should say next step, right? So next step is the current step is element 0. So next step is element 1 plus 1, right? Element 1 plus 1. So we say element 1 plus 1 is the next step. The next step is only 1 bigger, right? So it's equal to min step plus 1, right? If it's only 1 bigger, which means we can do this, because if it's 2 bigger, I don't need to do it, right? If it's 1 bigger, would it be impossible to do it? I don't think it's impossible. Well, it's a connected, right? Yeah, I think it is connected, because it's trying to, we want to answer the second minimum, which means, actually I'm not sure. You look great, by the way. Let me return 0. Yeah, I'm not sure. Like, let's say we don't have 4 to 5, right? If I don't have 4 to 5, what would this do? It's kind of an edge case. To reach all, oh, I think this is one of the requirements which says it can be reached. Okay, yeah, that's fine. So yeah, if that's, then I will visit the next edge. And what do you mean by that? Now, what I mean by that is, so I have min steps, but I will never update the min step, right? I will update the min step. I shall do this. I shall do if it has been reached twice, okay? Because if it has been reached twice, then I know. Okay, so boolean n reached twice, right? Reached twice is false. Initially is false, okay? And here I want to change it. If min steps child is equal to 0, okay, then what I will do is min steps child will equal to element 1 plus 1, okay, and I need to put into the queue. So queue dot add new int child and hold on, so it's an int next step is going to be element 1 plus 1, right? So we should say this equal to next step, and this will be next step. Oh, I think I should first check. So it would be this in the next int current node, right? Current node is equal to element 0, all right? And now we say if current node is number reached, right? We can say int reached count, okay? We do reached count. If current node is equal to n, then reached count plus plus, okay? But we keep going. It's fine, right? We keep going. We keep going. And then we compute the next step, and then we say min child, if it's equal to 0, then we set the next step, we put it in, right? And then we say else if, okay, else if, oh, oopsie doozy. Oh, redo. Right, we say else if element 1, which is next step, is equal to minimum this plus 1, right? If that's the case, I do not update. I simply just add a new int. I just add it to it. I just simply add to it. We just have another allowance, okay? We have another allowance. I'm wondering if this can be simplified, this logic. Okay, so we both have to add to the queue. All depends on if the min child is equal to 0, right? All depends on the min child is equal to 0. You know what? This has to be simpler than this. It has to be simpler than this. What if I don't set it to 0? Okay. What if I say arrays.fill min steps integer.max value? It shall be able to. There's no long, right? Everything is int. Okay. Let's say we do this. Okay. And now I think we can combine these two together. Oh, we basically just say, you know, if or if current steps, right? So you say next step is smaller than this, right? If next step is smaller than this, maybe smaller or equal to this, or it's equal to this plus 1. Okay, maybe we do this, right? If we say if it's smaller or equal to this or this, then we say this shall equal to math.minimum min steps child and next step, right? because this is what we want, and then we add this. Yep, this looks promising, right? We add it to it, and then we go back and we go back. We just keep going. But if the next step becomes more than one big then child, then we don't do it, right? Then we don't do it. So we do this multiple rounds. Okay, we do this multiple rounds. Maybe I don't need to use this. Maybe I can just go element 0, right? Next step, a bunch of next step. Okay, and then when we get out, I will have the min step saving the minimum step, and I can check, right? So I can check what? Second min step shall equal to reached count. Okay, so int second min step shall equal to reached count. Is it equal to 1? If it's larger than 1. If it's larger than 1, then it will be, which means it reached twice, right? It reached twice, so everything is just one step more. And if it reached twice, then we shall say min steps n plus 1. Otherwise, min steps n. Okay, so now I have the steps. Next is just to do this time and change crap. Okay, so now I say I have an int res equal to 0, and because I know the step, right? For int I equal to 0, I smaller than second min step I plus plus, right? So each time the current allowed will be change times I, right? Change times I, and also have time, right? So we start, so we have a time. So int current time shall be 0, right? Current time is 0. So if current time is 0, so the first step, right? We have a first step is going to be 0, right? And then the next one, I mean, it's not a current step, right? It's just the if I have 2 steps, then when we start counting, we go to the first one. So maybe I should do this, right? It should be 1 to smaller equal to, okay? And then we always rest. So we're hitting this. So we do this thing. We do this time. So plus equal to time, okay? And then not rest as a current time. Yeah, current time is rest, right? It's just a rest. It's just rest. Rest plus equal to time. And then if rest is larger than change times I, right? Because this is allowed. If this is larger than change times I, then rest shall equal to change times I plus 1. Because I need to wait for the next time to leave, right? Then I come back for the next time. Hold on. Well, what I'm trying to say is, if I go right, and that's the first step after current time, and if I'm bigger than, then I have to wait until this time. Wait until the next time to go, right? I have to wait until the next time to go. So there must be 2 things. So it shall be the change, right? So the change j, okay, j equal to 1, right? J equal to 1. So we shall say, let me see, j, right? Then I think we can do this. Can we do plus plus j here? So if res is larger than plus plus j, we have to wait for that, and then we go up because I added, so it must be bigger than, right? Because I already times plus plus j, so it will be the next time, right? It will be the next time. Why don't you just, just plus, right? Yeah. Green time, okay? So green time is change, right? So we do that. So if res is larger than green time, then we say green time plus equal to change and the rest equal to green time, which is the next green time. So we go back up. So next step with plus time, and I check. How do I handle this? Because if I go and then the green, if res is larger than the current green time, then we have to wait. So green time, and then I come back, res is smaller than green time, then I add the result. Right now we add it, and next one come, and then we'll add the green time. So if the green time is a big, right, we add a chunk of green time, right? So we need to have the current tick, right? We have a tick. Okay, so I have a tick, and then we'll add the time. So this is the current tick when we reach the next one. Then we need to know what are we in the waiting time or are we not in the waiting time? That's the one. We need to check if we are in the waiting time or not in the waiting time. How do we do that? Well, if it's a zero change, like we like that, right? So whenever we have hit a time, and if it's smaller, hold on. So current change, it's green, is 0 to this is green. Yeah, hold on. I think we need to be a little bit more specific, right? So let's say 0 to 5 is green, and 5 to 10 is bad. 10 to 15 is green, and this is bad. So basically, the good time is 0. 10, these are the good times. 0 is a good time. If you hit, 0 to 5, right? 0 to 5, 10 to 15, 20 to 25. These are the good times. So if you land in the bad time, then you are bad. You have to wait until the good time. And in this case, we have 3, which is a 6. Right, we end in the bad time, so we have to wait, right? Basically, it means it has to be even, right? 0 to 4, right? So the time, if we divide, right? If we divide change, it has to be even. If it's even, then we can go. If it's odd, then we have to wait for the next round. Okay, so basically we're gonna have res. We don't need this. And every time, hold on, let me just delete all of this, right? Right, so, well, plus equal to time. Actually, we can just go regular. Plus equal to time. I would say if res divided by change mod 2 is even equal to 1, not even if it's odd, right? If it's odd, then rest shall equal to what, right? Shall equal to what? Well, shall equal to shall equal to, all right, so int temp rest divided by change. Okay, then we can say temp, if it's even, then rest shall equal to temp plus 1 times change. Then we go back, then we add, and at the end we'll return rest. All right, let's try this one. Lots of analysis, and we'll see if it come back good. Take a look. Oh, okay, this is a bad example, so I need to use example. Try it again. Now it's not correct on the second one. It's not correct. We shall probably let's say system.print line, not dot out dot print line second minimum step. All right, let's see what this one print out. First one is 1. Second one is first one is 3. Correct. 1. Correct. Correct. I am pretty sure that this shall be. If it's larger than 1, we do otherwise. Ooh, plus 2. My bad. Plus 2. Right? And then think this one needs a comment. If we can reach n multiple times using the BFS scheme above, right? That means we can reach it in min step and min step plus 1 steps. Otherwise, the second minimum step, that means we can reach it, that means the second min step to reach it is min step plus 1. Otherwise, the min steps to reach n is to perform a back and forth, which means we will reach it in min step plus 2. Almost. I think the problem now is just with this. Okay, I think will be 3. Rest is 0. And then 3 will plus 3. Now it's 6. Okay. And 6 divided by 2 is 3. It's even. So we have to wait until what? Until, hold on. So basically we say 0, 2, 4, 6, 8, 10, right? So the first one is 3. First one is 3, okay? And 3 divided by 2 is 1. 1 is bad. So 1 plus 1 is 2. 2 times 2 is 4. So rest become 4, right? And the second one will become 4 plus 7. 4 plus 3 is 7, right? And the 7 divided by 2 is 3. So it shall be 8, right? And 8 plus 3 is, I see, I added one more. Which means I think I shall do it this, maybe -1. because the last step, after I do it, I don't have to commit it one more time, right? I don't have to commit one more time. So this is basically prepare for the next round to go after I add, right? So the previous one, I add a time, and if I need to do it, I hit it. If I don't, so I should say rest plus time, because the last one I don't really care. Once I reach there, then that's it. Okay, let's see. $44. $2045. So, what is this idea? Use a BFS that allows the visit of a node if it is the first time, which means we are finding the minimum path to reach it, or if the path to reach it is just one more than the minimum path. This guarantees that when n is reached, it is either reached with the min path or the min plus 1 path. Now if min plus 1 path is possible, right, from 1 to n, then that is the second minimum. If not, we need to do a back and forth such that the second minimum is minimum plus 2, right? Then based on the second minimum steps, we can compute the time, right, with the help of the given time to go, the time of each edge, and the change frequency of traffic light. I call it ON. ON times time. Yeah, ON. And we can actually do so. Yeah, here is actually, we can do this, right? We can do, say, if reached count is larger than 0, no, it's larger than 1, right? Then we just break, right? Only need to know if n can be reached once with min plus 1 step. So we can save some time here. The first time, then the second time, yeah. Okay, now we have assembled everything. Let's try. Hopefully this will pass. It does not. Okay, let's take a look. What went wrong? All right, so this is not going to look good. This is going to look bad. Did we pass some at least? We passed 74 out of 76, so it was pretty good. Probably just a little bit bug that we need to deal with. So what we have is 3 to 4, 2 to 4, 2 to 1, 5 to 4, and 3 to 1. All right, we need to rearrange them. So 2 to 1, 4, 3, 4, and 5, like that. Right. So we have 3 to 4, 2 to 4, 2 to 1, 5 to 4, 3 to 1. And we have time is equal to 5 and the change is equal to 1. Okay, output 23, expected 29. And then we need to go from 1 to 5. So I have 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5. So I think the second min step shall equal to 5 because there's no 1 to reach it, right? Because I go here, go back, and it's 2 steps. That's just no good. Here, here, here. So it's 5, right? Okay. So now we say min step is 5. So the first step is 5. And we need to wait until 6 to go, right? The first step. Second step is going to be 11, right? We need to wait until 12. Wait, hold a second. 1, so 0, 1, 2, 3, 4. So at each time I can go. Okay, the zeros, and then at 1, and a 2, right? At a 3. Wait, what does this change? I think I still got this change wrong. When the journey starts, all the signal is green, right? So I take 5 minutes to go to the next one. But a 5 is good, so I can just go 5, 5, 5, 5. Shouldn't it be like 20? But its output expect is 29, which means we need to add 4 in between. Alright, it's 0 to 1 is good, 2 to 3 is good, 4 to 5 is my bad. I got a little bit confused. And 1 to 2 is bad, right? So you have to still, so we get a 5, which is bad because it turns into red. So I have to wait to 6. And the second one will be 11, which is bad. I have to wait to 12. Third step basically is 17, which is bad. So I will wait to 18, right? And the fourth step is 23, which is bad. I have to wait to 24. And the fifth step is 29. It should be 29, but I got a 23, which I don't know why. The best way to know is to come here. I see. I see why. Dude, I see why. Because I get it out. I thought it's +1, but it actually should be +2. Dang it. Okay, so I need a better way because this basically reach at the same time, right? They basically reach at the same time. Whew. Yeah, I basically reach at the same time. I need to know. I need to know. How do I know? Yeah, I cannot count the number of time it reached. I need to know when it's reached, what is the step. Right? I need to know what the step is. And then I need to compare. Right? I need to compare. I need to compare. Well, how about that? Every time it's n, I will check, right? I will check if the current step, right? Because if the current step is 1 more, then I will count. Okay, so it'll be like this. If this is equal to n and element 1, okay, is equal to, right, is equal to min steps element n plus 1, then I can basically just break, right? I can basically break. Ah, yes. Then I can say boolean second min reached with second min. Okay, so when this happened, then I can say reached with second min equals true. Then I break. Right? If it's not true, that means it's just first time I reach. Right? First time I reach, but it does not matter. It does not matter. We just keep going. And then here I can say int this, right? We say second time, second reached, right? Reached with second min, right? Reached with second min. If it's true, then will be min status plus 1. Correct. If it's false, will be this. Okay, now let's test all these and let's see if this one's right. See, it's correct. Okay, now let's gonna run it. Voila. It passed. Slow. Alright, I don't know why it's so slow, but it worked. This idea worked. Now, it's slow maybe because, actually I don't know why. Maybe because I don't have to go through all the, I call it ON. Actually, I shouldn't call it ON. It's probably not ON. That depends on how many times I have to run this. I don't know. Honestly, how many times I have to run this? I call it ON. It's probably not true. I mean, the general BFS is ON, right? And I'll give all the chances of a second chance to be ON, but how many second chances I can give, right? How many second chances I can give? It basically, go back, so maybe, yeah, maybe I should say ON squared. Actually, I don't know. I do not know that, so we probably need to check the solution. There may be a better way. There may be a better way, but I did break out fast, right? I did break out fast, but I have to keep checking, right? I have to keep checking. There's no other way. I have to keep checking. Or maybe I should say if it's smaller, right? Maybe I should say if it's smaller instead of smaller or equal to. Maybe I should say smaller. Yeah. Because if it's equal to, then you are repeating yourself. And that was the problem. You're repeating yourself. And if I just say smaller, then let's try it again. This may be faster. Slightly. Slightly faster. All right, but I mean this idea works. So we're going to check the solution. Dijkstra. Should have thought about it, because this week is all about Dijkstra. Well, should have thought about Dijkstra. BFS M plus E. Is this the way that we're doing? Ah, yes. Yes, that's my idea, right? That was the idea that it's unweighted. Uh-huh. Yes. One, followed by all paths that are 2 edges away. Uh-huh. I don't have to worry about that. I just need to see if there's any difference in the computation of post distance 1, distance 2. First time, so update, yes. They just have another one called dist 2. Yeah, it's because it's equally weighted. I feel like this is about the same as how I'm doing it, right? I think that's about the same as how I do it. Because it basically just use two weights, right? I'm using 1, it's using 2. And it's trying to do distance 2. Yeah, I know what it's trying to do, right? So basically, if dist 1, which is the shortest path, if it has not been filled, you fill it. If dist 1 has filled, we check dist 2. If 2 has not filled, you fill it, right? If 2 has been filled, then you don't do it. And then at the end, you get, yeah, but what I don't like is, yeah, you mix the 2 logic together. This I don't like. So I separate them, right? I find the second minimum path first, and after I find it, I do this to compute and separate them, and it makes it clearer. Now I have to go back to the Dijkstra, see what. So basically, they're using Dijkstra, the modified Dijkstra, to find the second, right? To find the second. I think they're still using 2 distance arrays, the shortest and the second shortest. Oh, for any node except the source node, this and this are iterated with infinity. Okay, maintain a priority queue, sorting the node, the shortest distance, and also its second shortest distance. Whenever any of x's neighbor is popped out of the priority queue, if the total distance to x by the neighbors is less than this is updated and I push the queue. Yes. I also will try to update this if possible and push. So it's the same. It is Dijkstra, but with two distance arrays. Okay, 2 distance. If the shorter distance gets it, we'll do it. And if the shortest distance, if the current distance is bigger than the shortest distance, we check for the second one. So by doing that, we get the second minimum. Yes. It pops out a second time. We have the second minimum, so we do this. I see. Now this can be computed separately. I don't think it matters that much. Yeah, mod 2, you see? Mod 2. Then you do this, green light just to pass, yeah. But, okay, I'm not gonna do this because I think it's the same idea. It's just Dijkstra it. So what I will do is just Dijkstra to find the number of steps, and I will do this one again. So yeah, I think it's the same idea, similar. Okay, good, we solved it. But we don't have time to dig into all the other problem that's still wait to be solved. All right, anyway, I will end right here and see you guys tomorrow.